lecture is exclusively on conjugate direction methods for unconstrained optimization problems. In the previous two lectures, we were discussing the Newton's method and quasi-Newton methods, where we have seen that across the iterations we require the computation of the inverse Hessian matrix or an approximation of it. But you know, this computation of the inverse Hessian matrix or an approximation of it, they require quite a bit of computational cost. In conjugate direction methods, what we aim for? We aim for bypassing this calculation of the inverse Hessian matrix across the iterations with the help of a given set of conjugate directions with respect to the Hessian matrix of the objective function. We note that to solve unconstrained optimization problems, so far we have gone through the steepest descent method, the Newton method and quasi-Newton methods. Although Newton and quasi-Newton methods perform better than the steepest descent method, but they need high computational cost because they need computation of Hessian inverse or its approximation. In this lecture, we will introduce the conjugate gradient method, which is one between the steepest descent and the Newton method. Conjugate gradient method actually deflects the direction of steepest descent minus gk by adding to it a positive multiple of the direction being used in the last step. That is, we add with minus gk some constant multiplication of the direction dk minus 1, the direction which we have used in the previous step. And the conjugate gradient method only requires the first order derivatives but overcomes the steepest descent method's shortcomings of slow convergence. At the same time, conjugate gradient method need not save and compute the second order derivatives which are needed in Newton or quasi-Newton methods. In particular, since it does not require the Hessian matrix or its approximation, this conjugate gradient method is widely used to solve large-scale optimization problems. Where by large scale we mean the number of variables of the problem is quite large. This conjugate gradient method actually was originally proposed by Hestinus and Stiefel in 1950s to solve a system of linear equations of the type some matrix Q times some vector x, an unknown vector x plus some known vector b is equal to 0. To solve such a linear system of equations, Hestinus and Stiefel in 1950s gave the conjugate gradient method. But you notice that solving a system of linear equations, this qx plus b is equal to 0 is equivalent to minimizing a positive definite quadratic function half x transpose qx plus b transpose x plus some constant, say c. And as identification of a minimizer of this quadratic function is equivalent of solving this system of linear equations, Fletcher and Reeves in 1960s modified the conjugate gradient method for system of linear equations to solve unconstrained optimization problems with quadratic or non-quadratic functions. In this lecture, we aim to discuss this conjugate gradient method, and neatly the agendas of this lecture are at first the discussion of conjugate direction method, which in turn will give us the conjugate gradient method for quadratic function and for non-quadratic functions. Towards the end of this lecture, we will get to know several properties of conjugate gradient methods. Those are convergence nature, the local convergence rate, the global convergence analysis, the descent property or the quadratic termination property of a conjugate gradient method. Let's start our discussion with the basic conjugate direction method. Then from the ideas of conjugate direction method, we will discuss the conjugate gradient method. At first, let me discuss what do we mean by conjugate directions. Conjugate directions are associated to some given positive definite symmetric matrix. So let's suppose we are given a real symmetric positive definite matrix say Q of order n by n. Corresponding to this matrix Q, two non-null vectors say x and y in the n-dimensional Euclidean space Rn are called Q orthogonal or Q conjugate if the vector x is perpendicular to the vector qy, that is x transpose qy is equal to 0, and a set of n non-null vectors say d naught d1 till dn minus 1 from the n-dimensional Euclidean space Rn is said to be Q conjugate if any pair of vectors from this set, that means di and dj, say this di dj are Q orthogonal, that is if for any I not equals to j with ij being chosen from the index sets 0, 1, 2 till n minus 1, we have di transpose q dj is equal to 0. So if any pair of vectors taken from this set are Q orthogonal, then we call this set of non-null vectors Q conjugate with respect to the matrix capital Q. From this definition of Q conjugate directions, we have an immediate result that a Q conjugate set of vectors is linearly independent, where this matrix Q is a positive definite and symmetric matrix. And to prove the result, we assume that this matrix Q is of order n by n. To prove the result, let us start with a given d naught d1 d2 set till dp, this set which is known to be Q conjugate directions. Here this index number p is certainly less than equal to n, because if you have a set of more than n many vectors, that will be linearly dependent in the n-dimensional Euclidean space, and therefore this index number, this p or the number of vectors in this set, is less than equal to n. Now to prove that this set is linearly independent, we consider the equation alpha naught d naught plus alpha 1 d1 plus so on till alpha p times dp is equal to 0, where this alpha naught, alpha 1 till alpha p, they are scalars. Here this right hand side by 0 we mean the 0 vector or the null vector. We consider this equation and we will prove that all these alpha i's are to be 0, then only this equation is satisfied. And that will prove that this set is linearly independent set. So we consider this equation that I have written over here, and now to prove that all alpha i's are equals to 0, we pre-multiply on both the sides by say dj transpose q. Pre-multiplying by dj transpose q for some j in between 0 to p. This pre-multiplication will yield that alpha j times dj transpose q times dj is equal to 0. Because all these vectors are q conjugate, and hence for any I not equals to j, we have dj transpose q di is equal to 0. And therefore when we pre-multiply by dj transpose q on both the sides, we will get the leftover term on the left hand side as this term, and rest of the terms are all equals to 0. and therefore this further gives that alpha j is equal to 0 because Q is a positive definite matrix and then this term is a positive quantity and hence we get alpha j is equal to 0. Now the arbitrariness of the choice of j in between 0 to p gives that this alpha j is equal to 0 for every j in between 0 to till p, and therefore we get that for every j is equal to 0, 1, 2 till p, we have alpha j is equal to 0 and hence the result follows. Here as I have taken the index number starting from 0, so I must here consider p is strictly less than n, not less than equal to n. Now with the help of q conjugate directions, we aim for minimizing a quadratic function given by the expression say fx is equal to half times x transpose qx minus b transpose x plus c, where as usual x is a generic variable in the n-dimensional Euclidean space. The matrix Q is a symmetric matrix and positive definite. The vector B is a constant vector in Rn and C is a real number. Notice that a minimizer of this function f is given by the gradient of fx is equal to 0. A solution of this equation gives a minimizer or a minimum point of the function f. And this equation in turn gives us qx is equal to b, or the vector that minimizes the function f is given by x is equal to q inverse b. And let us suppose we name it this point q inverse b is equal to x bar. We notice that the computation of x bar requires the computation of q inverse, which is really costly, and therefore a question comes how to bypass the calculation of this q inverse. And interestingly, with the help of n many q conjugate directions, we can actually bypass the calculation of q inverse. This bypassing of q inverse can be done in the following manner: that to bypass the calculation of q inverse, we consider a set of n many q conjugate directions. Let's suppose these n many q conjugate directions given to us is the set d naught d1 till dn minus 1, which is a set of n q conjugate directions. And let us suppose we denote the vector q inverse b is equal to x bar. This x bar is just a hypothetical notation. We actually will not compute this q inverse to get the vector x bar. This is just a hypothetical notation x bar to mean that it is the vector q inverse b. Now to find the vector x bar without computing q inverse, we proceed as follows. We here note that this set of n vectors is a set of linearly independent vectors, and therefore the vector x bar can be expressed as a linear combination of these n many vectors. Let us suppose to express the vector x bar in terms of linear combination of the vectors d naught d1 till dn minus 1, we have say x bar is equal to alpha naught d naught plus alpha 1 d1 till alpha n minus 1 dn minus 1 for some scalars or real numbers. These real numbers alpha naught alpha 1 till alpha n minus. So here noticing that this set d naught d1 till dn minus 1 a set of n linearly independent vectors and hence is a basis of Rn. We can write the vector x bar in this manner. Now here to obtain these scalars alpha naught, alpha 1 till alpha n minus 1, we consider to pre-multiply on both the sides by say q dj transpose, which will give from this equation that on the right hand side alpha j times dj transpose q dj. Because this set of vectors d naught d1 till dn minus 1 is a set of q conjugate directions, and hence we get here that alpha j is given by dj transpose q x bar divided by dj transpose q dj. This will be true for every j 0, 1, 2 till n minus 1. And therefore the vector x bar is given by summation of alpha I di. I is ranging from 0 to n minus 1 is equal to summation over I equals to 0 to n minus 1. This alpha I is given by this expression, which gives us di transpose this qx bar. This qx bar is given by this equation, the vector b. So this di transpose b divided by di transpose q di times the vector di. Now here this term in the denominator is a scalar and the numerator is a term of the form a vector transpose another vector b times the vector d, which can be written as d transpose b. You please cross check this calculation. I am keeping it as a home task to verify that for any given two vectors in the n-dimensional Euclidean space d and b, you consider d is having components say d1, d2 till dn, and b is having components b1, b2 till bn. Then you just go for calculating the vector in the left hand side and check that that will be identical with the expression the vector in the right hand side. Fine. Here you notice that this d transpose is a matrix, and this matrix is multiplied with the vector b. So on the right hand side we will get a vector. Now we consider to employ this fact to write the expression of x bar, the summation I is equal to 0 to n minus 1. Now this di transpose b di can be written as di transpose this matrix multiplied with 1 over di transpose q di whole multiplied with the vector b. Now we notice this expression and this expression of x bar. We notice that this matrix actually mimic the matrix Q inverse, and by multiplying this matrix with b we are getting the vector x bar. So we don't need any computation of q inverse. You just need n many directions d naught d1 till dn minus 1, those are q conjugate. With the help of those vectors you consider to compute this matrix and then multiply this matrix with the vector b, you are going to get the vector x bar. So this is very fascinating that you don't need any computation of inverse of some matrix. You just need n many q conjugate directions, and with the help of any n many q conjugate directions, you can effectively identify the vector x bar, which is a minimizer of the quadratic function f(x) is equal to this entire expression. So now question comes, how to identify a set of n many q conjugate directions? Given a positive definite symmetric matrix Q, how do we find n many q conjugate directions? Let us endeavor to identify next a set of n many q conjugate directions for a given positive definite symmetric matrix capital Q. To find a set of n many q conjugate directions, we will follow the process analogous to the Gram-Schmidt method to find an orthogonal basis from a given any basis of the n-dimensional Euclidean space. So we proceed as follows. Let's suppose this set of vectors, say v naught, v1 till vn minus 1, be a collection of n linearly independent vectors from Rn, and the matrix Q, as usual, is a symmetric n by n matrix that is positive definite. Given this setup, let us now define a set of vectors d naught d1 till dn minus 1 in the following manner. We start with letting the vector d naught is equal to the vector v naught, the initial vector or the vector v naught that appears at the first in this set. And then we consider to define the next vector d1 given by v1 minus some scalar multiplication alpha naught times the vector d naught. Here, as we are going to identify q conjugate directions, these two directions once we have defined d naught and d1, they must be q conjugate, and hence from the equation of q conjugacy of the vectors d naught and d1, we get that d naught transpose q d1 is equal to 0, which yields d naught transpose q v1 minus alpha naught times d naught transpose q d naught is equal to 0, and hence we get the scalar alpha naught is equal to v1 transpose q times d naught divided by d naught transpose q d naught. Next we define the next vector d2 as the vector v2 minus a linear combination of the previous vectors d0 and d1. So we take the expression here that v2 minus some scalar beta naught times d0 minus some other scalar beta 1 times d1, where this beta 1 and beta naught, they are scalars. As we need this vector d2 to be q conjugate to d0 and d1, we get from the equations of q conjugacy of d2 and d0 and of d2 and d1 that d0 transpose q d2 is equal to 0 and d1 transpose q d2 is equal to 0. These two equations yield that just a straightforward calculation will give us beta naught is equal to v2 transpose q d naught divided by d naught transpose q d naught, and the scalar beta 1 is given by v2 transpose q d1 divided by d1 transpose q d1. And in general, letting the kth vector dk is equal to the vector vk minus a linear combination of the previous vectors d0, d1 till dk minus 1, that is an expression of the type gamma naught times d0 minus gamma 1 times d1 minus so on till gamma k minus 1 dk minus 1, where all these gamma naught, gamma 1 till gamma n minus 1, they are scalars. We shall get these scalars as gamma j is equal to. We look at these expressions of beta naught and beta 1. We notice that this beta naught is associated to d naught, and hence we have here this d naught, and in the denominator d naught transpose q d naught. And here, as we have the vector v2 to define the vector d2, we have v2 transpose being multiplied here. Similarly, for beta 1, as it is associated with d1, we have in the numerator this d1 transpose q d1, and here also this d1. And as in defining d2, we have taken this v2 here. This V2 transpose is multiplied over here to get the coefficient beta 1. Similarly for gamma j, as this gamma j is associated to dj, we will have in the numerator dj transpose q dj. In the denominator we have q dj to be multiplied with the vector vk transpose. This is for every j. J is equal to 0, 1, 2 till k minus 1. So by applying this recursive relation for k is equal to 0, 1, 2 till n minus 1, we are going to get the vectors d0, d1, d2 till dn minus 1, which is a set of n many q conjugate directions. And once n many q conjugate directions are identified, we can go for these n many q conjugate directions to identify a minimizer or a minimum point of a quadratic function whose Hessian is this matrix, the capital Q matrix. In fact, in finding a minimizer of a quadratic function, what we do, we identify a set of n many q conjugate directions, then starting from any arbitrary initial point x0, we minimize the function f along these n many directions. That is, starting from x0, we move along the direction d0, we take a step length of certain amount, say alpha naught, and then we reach at the point x1. Then after reaching at x1, we move along the direction, the next direction in the q conjugate directions d1, and take a step length of certain amount, let's suppose alpha 1, we reach at the point x2 and so on. And fascinatingly, at the end of visiting these n many q conjugate directions, we actually reach at a minimizer of the quadratic function. This visit along n many q conjugate directions gives us an optimization algorithm named as conjugate direction algorithm to solve an unconstant optimization problem with quadratic function. Let me now write out this conjugate direction algorithm to solve an unconstant optimization problem with quadratic function. For this algorithm of conjugate direction method, we start with a given initial point, say x0, and a set of n many q conjugate directions d0, d1, d2 till dn minus 1. Then iteratively we visit all these directions by the iterative formula, say xk plus 1 is equal to xk plus alpha k dk, where this alpha k is given by the exact line search method, that is alpha k is argmin of the function f along the direction dk emanated from the point xk. And as this function f is a quadratic function, we know that the expression of alpha k is given by minus gk transpose dk divided by dk transpose q dk. This is an easy exercise. You just try to find the explicit expression of f in terms of alpha and then take the derivative of this function with respect to alpha. You are going to get the expression of alpha k is equal to this, that gives a minimum point of the function f along the direction dk. I am keeping then this as a home task. So by this iterative formula, we go for finding the iterative points starting from x0. You find x1 by minimizing the function f along the direction d0, and then go for finding the next iterative point x2 by minimizing the function f along the direction d1 and so on. So we compute this iterative formula for n many times, that for k is equal to 0, 1, 2 till n minus 1. We compute this equation, and at the end we are going to get the point xn, which fascinatingly gives us the minimizer of the function f. Here you notice that as we have used q conjugate directions denote d1 till dn minus 1, the name of the algorithm is conjugate direction algorithm. We observe that this conjugate direction algorithm terminates within n many steps by producing xn, which is a global minimizer of a quadratic function. And therefore, certainly, this conjugate direction algorithm is having quadratic termination property. We shall now prove this quadratic termination property of the conjugate direction algorithm, and that will certify that this xn is effectively a minimizer or indeed the global minimizer of a quadratic function with positive definite Hessian. We shall now next prove the quadratic termination property of the conjugate direction method. We neatly state the result as follows, that for any starting point x naught, the conjugate direction algorithm converges to the unique minimizer x bar that solves qx is equal to b in n steps. That is, the point xn generated by the conjugate direction method is equal to x bar. Let us try to prove this result. The proof of the result is as follows. We notice that from the algorithm of q conjugate direction method, we have xn minus x naught is equal to summation of k is equal to 0 to n minus 1 alpha k dk, where this alpha k is given by minus gk transpose dk divided by dk transpose q dk. We look at the algorithm here, and in the algorithm we have started the algorithm for x naught, and then we moved along the direction d naught to find the next iterative point x1, where this x1 is given by x naught plus alpha naught d naught, where alpha naught is given by this expression. And then after reaching at x1, we have taken the direction of d1, along which a step of length alpha 1 is taken, and so on. So you notice here that this xn is given by x naught plus alpha naught d naught plus alpha 1 d1 plus till ending up with alpha n minus 1 dn minus 1. So xn minus x naught is certainly given by this expression that I have written over here. Now in the conjugate direction algorithm, we are given n many q conjugate directions, and n many q conjugate directions is a basis of the n-dimensional Euclidean space Rn, and therefore we can write this vector x bar minus x naught as a linear combination of the q conjugate directions d naught d1 till dn minus 1. So x bar minus x naught can be written as the summation k is equal to 0 to n minus 1 of some beta k times dk for some scalars beta naught beta 1 till beta n minus 1. So as d naught d1 dn minus 1, this set of n many vectors is a basis of the n-dimensional Euclidean space, we can write x bar minus x naught is equal to this expression. Now to find these coefficients or these scalars, to express x bar minus x naught as a linear combination of di's, we consider to pre-multiply both the sides of this equation with, say, dj transpose q, and by pre-multiplying with dj transpose q on both the sides of this equation, we see that we are going to get dj transpose q times x bar minus x naught is equal to, on the right hand side we will left over with beta j times dj transpose q dj. we will left over with only this expression because of the fact that these vectors dk's are q conjugate. So we get here the scalar beta j is given by 1 over dj transpose q dj times dj transpose q times this x bar minus x naught. Let us write this x bar minus x naught as x bar minus xj plus xj minus x naught. This is then equal to 1 over dj transpose q dj times dj transpose q x bar minus qxj plus dj transpose q times this expression xj minus x naught. We notice that this xj minus x naught in the conjugate direction algorithm is given by alpha naught d naught plus alpha 1 d1 plus till alpha j minus 1 dj minus 1, and hence ultimately we get this expression beta j is equal to 1 over dj transpose q dj multiplied with dj transpose this vector qx bar is given by the vector b, because x bar is the exact minimizer of the quadratic function, and therefore qx bar is equal to b minus, here we rest over with qxj plus, here you notice that these vectors d naught d1 till dj minus 1, they are q conjugate with the vector dj, and therefore all these multiplications will give us 0 values. So we will have here plus 0, which is contributed by the second term over here. Now we look at this expression, and we notice that this expression is the negative gradient of the function f at xj, because the function f is given by half of x transpose qx minus b transpose x plus c. F is a quadratic function, and therefore the negative gradient of f at xj is this expression, and therefore ultimately the expression of beta j is given by dj transpose the gradient at xj divided by dj transpose q dj, and this expression of beta j is valid for every j is equal to 0 to till n minus 1. Now we look at this expression of beta j and this expression of alpha k's. We notice that these two expressions, this and this expression, they are identical when I take this j is equal to k, and therefore this beta k and alpha k, they are identical for every k in between 0, 1 to till n minus 1, and hence x bar minus x naught is identical to xn minus x naught, and hence x bar is equal to xn. So we write here that that is what exactly we wanted to prove, and hence conjugate direction method is having quadratic termination property. Not only this quadratic termination property, but also there is a fascinating result for conjugate direction methods that states that for a given set of n many q conjugate directions, say d naught d1 till dn minus 1, we have gk plus 1 transpose dj is equal to 0 for all j is equal to 0, 1, 2 till k, and this equation is valid for every k is equal to 0, 1, 2 till n minus 1, where this gk plus 1 is as usual the gradient of the function, a quadratic function, at the point xk plus 1, where xk plus 1 is generated by the conjugate direction method. So in conjugate direction method or conjugate direction algorithm, we have these result true for every k is equal to 0, 1, 2 till n minus 1. The proof of this result is a straightforward calculation, and I'm not going to prove this result. If you are interested, you can look at the result in the lemma 10.2 at page number 155 of the Chong and Jack's book, which I have referred quite a few of times in the previous lectures. And we notice that this result effectively says that the gradient of the function, the quadratic function, at the point xk plus 1 is perpendicular to all of these vectors d0, d1, d2 till dk, and therefore this gk plus 1 is perpendicular to the span of the vectors d0, d1 till dk, which geometrically says that the vector gk plus 1 is perpendicular to the trajectory of the movement of the conjugate direction method that we have moved so far till the point xk. That is, let's suppose after visiting so many points, we have reached at the point, let's suppose, xk minus 1. Then the movement of the trajectory of the conjugate direction method is that from xk minus 1 we visit along the direction dk minus 1, then we reach at the point xk, then we move along the direction dk and reach at the point xk plus 1. Then if we compute the vector gk plus 1, the gradient of f at the point xk plus 1, we can see that this gk plus 1 is perpendicular to this trajectory that has been visited by the conjugate direction method so far. That means if this is the plane consisting this dk minus 1 dk, then this gk plus 1 is perpendicular to this particular plane. That is, the angle of gk plus 1 with this plane is 90 degree. And in fact, with the help of this observation, we can prove that the function value at xk plus 1, which is given by minimizing the function f along the direction dk, which is actually the minimum most value of the function f of the expression x naught plus beta naught d naught plus beta 1 d1 till beta k dk, where this minimization is taken over these scalars beta naught, beta 1, beta k. So here beta naught, beta 1 till beta k belonging to the real number set. You minimize this function of this expression, you are going to get the function's value at the point xk plus 1. We notice that this minimization of this line is actually the minimization of the function f over the vector space vk, where this vector space vk is given by x naught plus span of the vectors d naught, d1 till dk. Due to this, fxk plus 1 is equal to this minimization of f over the vector space vk, we see that as k increases, this vector space vk gets expanded and eventually fills the whole Rn when this k is equal to n minus 1. So you are going to get the function value f at the point xn is equal to minimization of fx over the n-dimensional Euclidean space Rn. So by visiting from x0 to x1, we are trying to fill up the n-dimensional Euclidean space Rn by the subspace generated by the vector d0. Then by visiting the d0 d1, we are slowly filling up by two-dimensional subspace generated by d0 d1, and by visiting till the direction dk, we are filling up the n-dimensional Euclidean space Rn by the subspace generated by d0 d1 dk, and ultimately when all the vectors d0 d1 till dn minus 1 are exhausted, we have actually filled the entire vector space Rn. So as k increases, we are slowly, little by little, we are actually filling up the entire n-dimensional Euclidean space Rn in the conjugate direction method. As this vector space Vk gets slowly expanded and eventually fills the whole Rn, we usually refer this result by expanding subspace theorem. For a proof of this fact that I have written over here, that fxk plus 1 is minimization of fx over this vector space Vk, you may please look at the page number 157 of the Chong and Jack's book, where by a straightforward calculation you will find that this equation is valid. Now in the next we shall move forward discussing a method called conjugate gradient method for solving an unconstrained optimization problem with the objective function being a quadratic function. We notice that in the conjugate direction algorithm, to find the iterative points and reaching at the point xn that gives a minimizer of a quadratic function, we need a priori given in many q conjugate directions. But in conjugate gradient method, we actually do not use pre-specified n many conjugate directions, but instead we compute the conjugate directions as the algorithm progresses. The computation of conjugate directions in the conjugate gradient method as the iterative points are progressing, we follow the following procedure. That at each and every iteration, let's suppose iterative point xk, we define a direction dk that is given by the negative gradient plus a linear combination of the previous direction dk minus 1. That is, we take the expression of dk is given by minus gk plus bk minus 1 times dk minus 1, where bk minus 1 is a scalar. We take this scalar bk minus 1 in such a manner that this direction dk is q conjugate with all the previous directions d0 d1 till dk minus 1. As in defining dk, we use the gradient as well as conjugate directions. So these conjugate directions plus gradient gives us the name conjugate gradient method. The conjugate gradient method actually exploits the fact that for a quadratic function of n variables, we can locate the minimizer by performing n searches along mutually q orthogonal or q conjugate directions. In the development of conjugate gradient method, as before, we start with considering a quadratic function if x is equal to half x transpose qx minus b transpose x plus c, where this matrix Q is a positive definite symmetric matrix. To locate a minimizer of this quadratic function, our first search direction from an initial point x0 is the direction of steepest descent. That is, we take the direction as the gradient of the function f at the point x0. And after finding this d0, we go for computing the next iterative point x1 given by x naught plus alpha naught d naught, where this alpha naught is given by the exact line search, and hence the expression G naught transpose G naught divided by D naught transpose Q D naught. In the next stage, we search in a direction D1, that is Q conjugate to the direction D naught. We choose this D1 as a linear combination of the current gradient at the point x1, and the vector D naught. In general, at the k plus 1th step, we choose the vector dk plus 1 as a linear combination of gk plus 1 and dk. Specifically, we choose this dk plus 1 given by minus gk plus 1 plus beta k dk for some scalar beta k. The coefficient or the scalar beta k is chosen so that this vector dk plus 1 is q conjugate to dk. From this equation, we see that we have dk transpose q. The expression of dk plus 1 is given by minus gk plus 1 plus beta k dk, which is equal to 0, and hence the scalar beta k is given by gk plus 1 transpose q dk divided by dk transpose q dk. So in the process, you start with this direction d naught, then find iteratively the directions d1, d2, d3 and so on, where these coefficients beta k's are given by this expression that I have written over here. And by following this process, we can fascinatingly prove that these directions generated by this formula of beta k are actually q conjugate directions. We state this fact in a result which states that the directions generated as above, that is the directions d naught, d1, dn minus 1, are q conjugate directions, where this d naught is given by the negative gradient of the function at x naught, and iteratively d1 to dn minus 1 is given by this iterative formula that dk plus 1 is equal to minus gk plus 1 plus beta k times dk, where this beta k is given by gk plus 1 transpose q dk divided by dk transpose q dk for every k is equal to 0, 1, 2 till n minus 1. Fine. So with the help of this result, we can now devise a new algorithm where instead of pre-specified n many q conjugate directions, we can instead compute the directions, the q conjugate directions as the algorithm progresses, which is as follows. That you start from x naught, then you compute the vector d naught, next you find the vector next iterative point x1 by this equation, then reaching at the point x1, you find the direction d1 given by this expression, where beta naught is given by this expression by plugging k is equal to 0. So you have gotten the direction d1. Now after finding d1, now you compute x2 is equal to x1 plus alpha 1 d1, where alpha 1 is given by the exact line search by an expression of this type, and after reaching at x2 you compute d2 given by minus g2 plus beta 1 d1, where beta 1 is given by this expression, and so on. So in this way you start from the initial iterate x naught, then you compute the direction d naught, reach at the point x1, then reaching at the point x1 you compute a direction d1, that is q conjugate with the vector d naught, and by moving along the direction d1 you reach at the point x2. Reaching at the point x2 you consider to identify a direction d2, that is q conjugate with d naught and d1, and then you reach at the vector x3, and in this way you keep on finding the directions d naught, d1, d2 and so on, and ultimately reach at the point xn. Now here we notice that as these directions dn, dn minus 1, dn minus 2, d2 till d1 and d naught, as all these directions are q conjugate, certainly you will get this xn, a minimizer of the quadratic function f that you have started with over here. So the conjugate gradient algorithm does not use pre-specified conjugate directions, but instead computes the directions as the algorithm progresses. We now neatly write out this process, the process that I have mentioned over here, which is the algorithm of the conjugate gradient method. Neatly, the conjugate gradient algorithm for quadratic functions is as follows. The conjugate gradient method for a quadratic function is as follows: that given an initial point, say x naught, define the current direction d naught as negative gradient at the point x naught, then for k is equal to 0, 1, 2 till n minus 1, compute the next iterative point given by xk plus 1 is equal to xk plus alpha k dk, where the value of alpha k is given by the exact line search along the direction dk. So the expression of alpha k is gk transpose gk divided by dk transpose q dk. After computing this xk plus 1, go for computing the next direction given by dk plus 1 is equal to minus gk plus 1 plus beta k dk. So the scalar beta k is given by, we have already computed that gk plus 1 transpose q dk divided by dk transpose q dk. So for every k ranging from 0, 1, 2 till n minus 1, go for computing all these iterative sequences, and at the end, unless you get gk plus 1 is equal to 0, you are going to generate a point xn that is the minimizer of the function f. So these are the steps for the conjugate gradient method. In the conjugate gradient method, we have already seen here in this result that the directions d naught, d1, dn minus 1 generated by this formula, that dk plus 1 is equal to this expression, where beta k is this expression, will give us all these directions q conjugate. And hence in the conjugate gradient method we effectively follow a set of n conjugate directions, and hence conjugate gradient method is also a conjugate direction method. Here, for a proof of this result, you may please visit the page number 159 of the Chong and Jack's book in its second edition. I also mention here that conjugate gradient method is a conjugate direction method. Now, so far we have been describing conjugate gradient or conjugate direction methods for quadratic functions. Now we shall move forward to find conjugate gradient method for non-quadratic functions. Before that, let me give an example of the conjugate gradient method that is to be applied for a given quadratic function of, let's suppose, of three variables. Let me consider to apply conjugate gradient method on the function where the matrix Q is a 3 by 3 positive definite matrix given by this matrix, and the vector B is this vector. On this function, we go for applying the conjugate gradient method to locate a minimizer of this function with the initial point, say x naught is equal to the vector, the origin of the three-dimensional Euclidean space R3. In computing the iterative points of the conjugate gradient method, we notice that we need to compute the gradient across the iterations, and thus at the beginning we go for computing the gradient at any general point x. You notice that the expression of gx is given by this expression. Please verify it. And with the help of this gradient, now let us go for computing the first iteration, or the iteration for k is equal to 0. For k is equal to 0, the gradient at x0 is the vector -3, 0, -1, and hence the direction d naught in the conjugate gradient method is given by 3, 0, 1, because d naught is negative of g naught. Then we need to compute alpha naught given by g naught transpose d naught divided by d naught transpose q d naught. You please execute this expression. You will find that this expression gives us 10 by 36, and hence the next iterative point x1 given by x naught plus alpha d naught is equal to, numerically you please check, 0.8333, 0.2778. And therefore, to compute the next direction d1, the scalar beta naught is equal to 0.08025, and hence d1 is given by minus g1 plus beta naught d naught, which you please verify that is given by this vector. And with this vector d1, we go for computing the next iterate, that is for k is equal to 1. You go for computing alpha 1, then x2, then beta 1, and then d2. You will find that as a home task, I am writing out that the direction d2 is given by this vector, and ultimately at the iteration k is equal to n minus 1, that is k is equal to 2 here for this problem, the vector x3 will be given by the vector 1, 0, 0. Please verify it, and this x3 is the minimizer of the given function f. Now next we go for discussing the conjugate gradient algorithm for non-quadratic problems. We notice that so far in this lecture, we showed that the conjugate gradient algorithm is a conjugate direction method, and therefore it minimizes a positive definite quadratic function of n variables in n steps. The algorithm can be extended to general nonlinear function by interpreting the quadratic function as a second order Taylor's approximation of the objective function. And we all know that near the optimum solution of a non-quadratic function, the function behaves like a quadratic function. We notice that a quadratic or a quadratic function fx is equal to half x transpose qx plus a linear term. The Hessian of such a function f is a constant matrix, the matrix Q. However, for a general nonlinear function, the Hessian is a matrix that has to be re-evaluated at each iteration of the algorithm, and this can be computationally very expensive. Thus, an effective implementation of the conjugate gradient algorithm that eliminates the Hessian evaluation at each step is really desirable. Now we observe that the matrix Q appears only in the computation of the scalars alpha and beta. We look at this algorithm, the appearance of Q, the Hessian matrix, is only in the evaluation of alpha k and in beta k. However, the evaluation of alpha k in the algorithm can even be replaced by a numerical line search procedure, like any inexact line search procedure where we consider certain decrease conditions like Armijo rule or Wool-Powell rule or strong Wool-Powell rule or whatsoever inexact line search you consider. Those gives us certain condition which gives us a range of values of alpha, and you go for choosing any value from this alpha to b which satisfies one of the inexact line search conditions, then you choose that chosen alpha in between a to b as your alpha k. So in this way, the appearance of q or the influence of q in the evaluation of alpha k can be bypassed, and so we only need to concern ourselves with the formula for beta k. We need to find some way out so that the appearance of q might not be there in the expression of beta k, because otherwise at each and every iteration we need to compute this matrix q, which is not a constant matrix for a non-quadratic function. So the conjugate gradient method for a non-quadratic function has to be evaluated in such a manner that the expression of beta k does not involve the Hessian matrix of the function. And fortunately, you know the elimination of the appearance of this Hessian, the matrix Q, from the formula is possible, and that results in algorithms that depend only on the function and gradient values at each and every iteration. We shall now discuss modifications of conjugate gradient algorithm for a quadratic function for the case in which the Hessian is unknown but in which the objective function values and gradients are available. These modifications are actually based on algebraical manipulation of the formula beta k in such a way that the appearance of q is eliminated. And once the appearance of q is eliminated, we can then go for applying the expression of beta k for a non-quadratic function for which we will not have to evaluate the Hessian matrix. Three common modifications of the expression of beta k in the conjugate gradient method are the Hestinus-Stiefel formula, the polar gravity formula, and Fletcher-Reeves formula. We will consider to discuss all of these three formulas one after another. The Hestinus-Stiefel formula is identified in the following manner. We recall that the expression of beta k in the conjugate gradient algorithm for a quadratic function is given by from this expression we want to eliminate the appearance of q. For this we notice that q dk can be written as gk plus 1 minus gk divided by alpha k. Indeed, we can replace this q dk by this expression because we notice that gk plus 1 is the gradient of the function at the point xk plus 1. For a quadratic function, this gk plus 1 is then given by qxk plus 1 minus b, and similarly gk is given by qxk minus b whole divided by alpha k. That gives us q times xk plus 1 minus xk divided by alpha k, but xk plus 1 is given by xk plus alpha k dk, and hence we have here that this is equal to q dk, and therefore indeed this replacement q dk is equal to gk plus 1 minus gk divided by alpha k is possible, and hence we consider to express beta k in terms of the gradient that gk plus 1 transpose times gk plus 1 minus gk whole divided by alpha k, and in the denominator also we replace this q dk by this expression. So 1 by alpha k in the numerator and 1 by alpha k in the denominator will get cancelled, and ultimately we will end up with in the denominator dk transpose gk plus 1 minus gk. And in this expression we notice that there is no appearance of the matrix capital Q. So we can go for employing this expression of beta k for a non-quadratic function for which we do not need to compute the Hessian matrix at the current iterate xk. Two more modifications of the expression of beta k in terms of the gradient evaluation are as follows. The other one is Polar-Grevire formula. To identify the Polar-Grevire formula, we start with this expression of beta k of the Hestinus-Stiefel formula, and we notice that the denominator of the Hestinus-Stiefel formula can be expressed as the expression in the expanded format is dk transpose gk plus 1 minus dk transpose gk. Now we look at this expression. This expression is equal to 0. We have proved for a quadratic function. You please recall here the expanding subspace theorem that I have mentioned earlier, where I have stated that gk plus 1 transpose dk is equal to 0. Now let us look at this expression dk transpose gk. We notice that in the conjugate gradient algorithm, dk is taken as minus gk plus beta k minus 1 dk minus 1. Now if we multiply transpose of this vector with gk, then we notice that we shall get, we now apply once more the expanding subspace theorem. You will get that this gk transpose dk minus 1 is equal to 0, and hence in the denominator you rest out with the expression that gk transpose gk, and this term in the denominator, keeping the numerator as it is, gives us the Polar-Grevire formula of the scalar beta k. Here you notice that once again in this expression you don't have the appearance of q. Not only that, in this expression you also do not have the appearance of the vector dk. We can even further simplify this expression, and a further simplification of this expression of beta k, the Polar-Grevire formula, gives us the Fleischer-Gibbs formula, which is derived in the following manner: that you start with this Polar-Grevire formula Then consider an expanded format of the numerator, which is your gk plus 1 transpose gk plus 1 minus gk plus 1 transpose gk, where this expression by the expanded subspace theorem can be proven to be is equal to 0. It is as follows that we recall the expanded subspace theorem, where we have proved that gk plus 1 transpose dk is equal to 0. Now we consider to write the expression of dk, which is minus gk plus beta k minus 1 dk minus 1, and this equation further gives that gk plus 1 transpose dk minus 1 is equal to 0, and hence gk plus 1 transpose gk is equal to 0. Hence a further simplified formula for beta k is given by gk plus 1 transpose gk plus 1 divided by gk transpose gk. Here in the simplified formula for beta k, this Fletcher-Gibbs formula or this polar derivative formula, we notice that we have used the fact that gk transpose dk is equal to 0, where this fact is true for a quadratic function with positive definite Hessian. So all these formulae, this beta k for Fletcher-Gibbs formula, this beta k for polar derivative formula, or this beta k for Heston-Stiefel formula. All these are identical formulas, and they are all identical with this expression in the original conjugate gradient method for a quadratic function with positive definite Hessian. So all these formulas that we have derived, these three formulas for beta k, gives us conjugate gradient algorithms that do not require explicit knowledge of the Hessian matrix Q. And for a quadratic function, all these three expressions of beta k are exactly equal. However, this is not the case for general nonlinear objective functions. For a general nonlinear objective function, you may not have this expanded subspace theorem that these result holding to be true. And therefore, all these three expressions are not identical for a non-quadratic function f. If we are going to choose any of these beta k expression, let's suppose you are going to choose beta k expression given by this expression for a non-quadratic function, then using this beta k expression in the conjugate gradient method or here in the conjugate gradient algorithm, if you replace this beta k by say polar derivative formula, that you are replacing this beta k by gk plus 1 transpose gk plus 1 minus gk divided by gk transpose gk, and you are going to compute alpha k by one of the inexact line search methods, then you notice that you do not require the computation of the Hessian matrix for a non-quadratic function, and alpha k chosen by the inexact line search method and beta k given by this expression will give us a conjugate gradient method for a non-quadratic function. Once this formula is chosen, then we shall refer that conjugate gradient method as the polar derivative conjugate gradient method, and for a non-quadratic function, these entire step for k equals to 0 to n minus 1, we need to replace it by a while loop, that while the gradient at xk plus 1 has a norm greater than equals to a tolerance level epsilon, you keep computing all these steps, alpha k given by some inexact line search and beta k given by this polar derivative formula. You keep computing this xk, alpha k, beta k, dk unless and until you are going to get the gradient of the function at the point xk plus 1 is less than epsilon, and you will end up getting a point xk plus 1 at the end of this while loop, at which you will find that norm of gk plus 1 is less than epsilon. This is how a conjugate gradient method for a non-quadratic function works. Now replacing the expression of beta k by any of the three formulas, that Hestinus-Stephen formula, Fletcher-Gibbs formula, or polar-Gravito formula, you will get three conjugate gradient methods for non-quadratic functions. But for non-quadratic problems, the algorithm will usually not converge in n steps. And as the algorithm progresses, the Q conjugacy of all these directions being computed inside of this while loop for a non-quadratic function will tend to deteriorate, and thus a common practice is to reinitialize the direction vector to the negative gradient after every few iterations, maybe after n many or n plus 2 many or 2n many iterations. You reinitialize that the direction dn plus 2 is equal to the negative gradient at the point xn plus 2. Here I have taken in particular after n plus 2 many iterations of this while loop, we are going to reinitialize the vector d to be taken as the negative gradient. For a quadratic function, we just consider the initial vector to be negative gradient, but for a non-quadratic function, in every n plus 2 iterations or 2n many iterations, or in every n plus 5 iterations, or in every 2n iterations, you go for reinitializing the vector dk as the negative gradient at the point xk, and keep continuing evaluating all these steps in the while loop unless and until this stopping condition is satisfied. So for a non-quadratic function, this reinitialization of the direction is an important issue. Unless a reinitialization is used, commonly conjugate gradient method for a large scale problem does not work well. There is also one important fact, that if the Hessian matrix of a non-quadratic function is ill-conditioned, then a conjugate gradient method may not also work well for a large-scale problem. And to alleviate this ill-conditioning, we usually in numerical optimization employ a preconditioning method. In a preconditioning, what we do, instead of solving the problem in the x space, solving the problem of a non-quadratic function in the x space, what we do is that we transform the space in the x hat space given by Tx, where we choose the transformation matrix, an invertible matrix T, such that the condition number of the matrix T transpose the Hessian of the function times the matrix T has much smaller condition number than the matrix, the Hessian of the function F. You choose such a matrix T and then solve the problem in the x hat space. In the x hat space, the Hessian matrix is given by this matrix, which has smaller condition number, and hence the conjugate gradient method will work well in the space of x hat. This transformation of space from x to x hat is mathematically known as preconditioning. So a preconditioning and a reinitialization are to be used for a non-quadratic function to realize that for a large scale problem, conjugate gradient method works well for a non-quadratic function. Now next we shall go for the convergence analysis for conjugate gradient method. Before that, let me mention whether the conjugate gradient method is having the decency property. We got to know that the conjugate gradient method is a conjugate direction method, and hence the conjugate gradient method is having a quadratic termination property. But what about the decency property? Is a conjugate gradient method a decent method? To answer this question, we again recall here the expanding subspace theorem that this result gk plus 1 transpose dk is equal to 0 for a quadratic function with positive definite Hessian. And for a quadratic function with positive definite Hessian, we see that the direction dj in the conjugate gradient method times the gradient at xj is given by this dj is given by minus gj plus beta j minus 1 dj minus 1 its transpose times gj, which is equal to, we notice that is gj transpose times gj multiplied with minus 1. Because of this result, gj times dj minus 1 is equal to 0, and hence the direction dj is such that once we take inner product with the gradient vector at xj, we get a negative quantity, and hence certainly the direction of movement dj at the current iterate xj is a descent direction. So conjugate gradient method is a descent method for a quadratic function with positive definite Hessian. And you notice that the direction dk that is used in the conjugate gradient method is a deflected steepest descent direction, that negative gradient at xk plus a bit deflection, that we are adding beta k minus 1 times dk minus 1. So dk, the direction dk is almost the steepest descent direction, but deflected by a direction beta k minus 1 dk minus 1. And therefore, we may expect that this direction dk for a nonlinear function is going to behave at least as a descent direction, and hence there is a global convergence result of the conjugate gradient method even for a non-quadratic function. For a nicely detailed convergence analysis, the global convergence analysis of the conjugate gradient method with exact and inexact line search, I would like to refer you the detailed analysis given in the chapter 4 of the Sun and One's book that I have referred many a times in the previous lectures. In specific, you please look at the subsection number 4.3, where you will get a nicely detailed global convergence analysis of the conjugate gradient methods. Now, to sense a convergence rate of the conjugate gradient method, we shall demonstrate a result that indicates that the conjugate gradient method is not worse than the steepest descent method. In fact, the conjugate gradient method behaves well, far better than the steepest descent method, but not as well as the Newton's method. To sense a convergence rate or how fast is the conjugate gradient method, I would like to mention a result that for a quadratic function with a special expression, we are taking this special expression for our convenience of the discussion, that you take this expression of the objective function f, and then we can prove that the function value at the k plus 1th iterate for the steepest descent method is bigger than equals to the function value at the k plus 1th iterate of the conjugate gradient method. Here we are considering the step length in the steepest descent as well as in the conjugate gradient method, the exact step size. So we write here with exact step size, you compute the steepest descent iterates and you also compute conjugate gradient iterates, you will find that the function value at the k plus 1th iterate in the conjugate gradient method is lesser than or equals to the function value at the k plus 1th iterate of the steepest descent method. We shall end up this lecture by proving this fact, and this result will eventually give us a sense that the conjugate gradient method is faster than the steepest descent method. In proving this result, we recall here that the exact step size for a quadratic function along a given direction, say dk, is given by for a quadratic function that minus gk transpose dk divided by dk transpose q dk. So we obtain that the function value at xk plus 1, which is given by if xk plus alpha k dk is equal to half of xk plus alpha k dk transpose q times xk plus alpha k dk, which in turn gives us half of xk transpose qxk plus alpha k xk transpose q dk, because the matrix q is symmetric, plus half alpha k square dk transpose q dk, which is further is equal to half xk transpose q xk plus alpha k times, we write here that this entire expression is equal to transpose of it, because it is a real number. So dk transpose q xk, we can even replace this qxk by the gradient of the function. So we replace it by gk, because we have taken the expression of the function f as half x transpose qx. So we have the gradient gk is equal to qxk plus the last term is equal to half times dk transpose gk whole square divided by dk transpose q dk. Here we have plugged the expression of alpha k given by this expression. Now we consider to employ this expression of alpha k once more over here, and we will end up with getting this expression as half of xk transpose qxk minus half of dk transpose gk square of it divided by dk transpose q dk. So for any general direction dk, we see that the expression of alpha k is given by this expression. Once we are considering the step length to be taken by the exact line search, and considering this exact step length, the next iterative point xk plus 1 is given by this expression, the expression that we have gotten over here. Now if we consider the direction dk to be the steepest descent direction, that is the direction negative gradient, then we see that this expression of fxk plus 1 gives us fxk plus 1 steepest descent method is equal to this expression, that is the xk at the steepest descent method minus half of, now this dk has to be replaced by minus gk. So we end up getting the norm gk square divided by gk transpose qgk. Now for the conjugate gradient method, the direction dk is given by dk conjugate gradient, that is equal to minus gk plus beta k minus 1 dk minus 1, which gives that if xk plus 1 is equal to, if xk for conjugate gradient, this expression, minus, we shall go with a side calculation for the second term, for this term, that dk transpose q dk is equal to minus gk plus beta k minus 1 dk minus 1 transpose q times minus gk plus beta k minus 1 dk minus 1, which is equal to gk transpose qgk plus, you notice that the term involving this dk minus 1 transpose times gk is equal to 0, and hence ending up with bk minus 1 square dk minus 1 q dk minus 1. As this term is positive, because q is positive definite, we have to assume here that this q, as usual, is positive definite and symmetric. So we get here that is greater than equals to gk transpose qgk. Now we notice here that this dk transpose gk, once this expression of dk is employed over here, then due to the fact that gk transpose dk minus 1 is equal to 0, we will have then in the numerator norm of gk square divided by dk transpose q dk. Now as this dk transpose q dk is bigger than equals to gk transpose q gk, you will have here that this is less than equal to f xk cg minus half of norm gk square divided by gk transpose qgk. Now if we have started from the same initial iterative point in a steepest descent method and in the conjugate gradient method, then the function value, this function value and this function value at the initial iterate are same, and hence in the consecutive iterates this inequality will reflect that the function value at xk plus 1 cg is less than equal to the function value at xk plus 1 sd. This is what exactly we wanted to prove in this result, that the function value across the iterative points in the conjugate gradient method is less than equal to the function value in the steepest descent method. With this discussion of conjugate gradient method, I conclude here the section of numerical methods for unconstrained optimization problems. In the next lecture, we shall consider to talk about constrained optimization problems. We shall discuss at first the constrained optimization theory, necessary and sufficient optimality conditions, and then later on, with the help of the theories for constrained optimization, we will develop numerical algorithms for constrained optimization problems. I stop the lecture here. Thank you. Thank you all for all of your kind attention.